Hello friends and welcome to the course of Power Electronics in the Electrical CG channel. So in the previous videos, we have seen the reverse voltage current characteristics of power diodes, right? So from today, we will be starting a session on the forward voltage current characteristics of power diodes. Now, before starting with the characteristics, there are some very important concepts that you have to understand in this particular video. Now, let us start with a revisit on what was the drift layer. You know that drift layer the drift layer was having lightly doped. It was a lightly doped layer. And why it was introduced, I have written here. So the introduction of the drift layer in power diodes construction boosts the reverse blocking capabilities of the diode. That means the drift layer was introduced to boost the reverse blocking capabilities of the diode. So naturally there will be a question. Okay. So to understand that question, we have to see some basic idea. Now, what is the meaning of lightly doped? The lightly doped means the charge carriers will be less, right? The charge carriers will be less. So naturally, when charge carriers are less, you know that the conductivity will be less. And the conductivity is less, the natural consequence is that the resistance will be high. So the question that would come in everybody's mind is that if you introduce the drift layer, that does the drift layer introduce high resistance during forward conduction? The question is, does the introduction of the drift layer introduce high resistance during forward conduction? By this explanation, it does look like there is going to be high resistance during forward conduction. And high resistance during forward conduction means in the forward conduction, the power loss would be high. But the answer to this question, that does the drift layer introduce high resistance during forward conduction, is that the effective resistance of this region, that is the drift region in the on state or the forward conduction state, is much less than the apparent resistance calculated based on geometry and thermal equilibrium charge carrier densities. Let us understand this point properly. Now, what it tells, the effective resistance of the region in the on state. So I'll write that here. So the R effective of the drift region, during the on state, they are telling it is less than the apparent resistance. The apparent resistance which is calculated based on the geometry and the thermal equilibrium charge carrier densities. Okay, so what is R effective? This is the actual resistance of the drift region. Okay, if you have a way to measure that, it is the actual resistance of the drift region in the forward conduction state. And what is the apparent resistance? The apparent resistance, you can see it is calculated based on geometry. That means it is calculated based on this relation R is equal to rho L by A. So this L is a geometric factor, A is a geometric factor, and also it depends, the apparent resistance depends on the thermal equilibrium charge carrier densities. Naturally, you know, if you are having more charge carriers, the resistance would be less. So what they are telling here is that the effective resistance during the on state, that means this is the actual resistance, is much less than the apparent resistance, that is you are calculating using this particular relations, and the number of charge carriers, or we can call it as the charge carrier densities in thermal equilibrium. Okay, so the answer is simple. The resistance will not be high, the resistance will be low during forward state of the drift region. So how is this possible? That we have to see in the next slides, the explanation in the next slides. Now you are having here the power diode construction which I have shown here. So you can see that this is the P plus region heavily doped, N plus region heavily doped. This is the anode, this is the cathode, and you are having two, and this is the drift region. This is the drift region which you have talked about a lot. So you can see that between the P plus region and the N minus region, you are having the first metallurgical junction, which is the P plus N minus region. And between the N minus region and N plus region, you are having the second metallurgical junction, N minus N plus region. Okay. Now, when you are forward biasing this diode, what happens? Let us see. Now you see here, let us focus our attention here. So you know that the P plus region is heavily doped. So therefore, the P type charge carriers will be very high. In this case, p-type charge carrier means it will be holes. The p-type charge carriers will be very high in this region. Now you know that drift region is lightly doped. Okay, therefore here electron concentration will not be very high and holes concentration will be still lesser. Okay, so this is the electron hole concentration, this is the electron concentration, this is the hole concentration. Because this n-type material, you will have some electrons, less number of electrons due to lightly doping, and hole concentration will be still lesser. So what will happen here? Under the forward bias condition, the metallurgical p plus n minus junction, that means this junction here, there will be high injection of excess p-type charge carriers into the n side. Naturally, here you are having less holes, here you are having high holes, and you are putting forward bias condition. Naturally, using diffusion, because charge carrier will move from high concentration to low concentration, the holes, that is the p-type charge carriers, will move from p plus region to n minus region. P plus region to n minus region. Now, what if the injection is low? Let us assume a condition where the injection is low. Injection in the sense how much of p-type charge carriers are moving from p plus to n minus side. Let us define a term which is delta p. Delta p is the injection of the p-type charge carriers, p-type charge carriers from the p plus region to n minus region. And let us call here the charge density in the charge distribution of the in the drift region. We will call that is ND0. Okay, N because these are electrons, D is for drift region, and 0 is showing for thermal equilibrium. So the first case here is when delta P is less than ND0. That means the electron concentrations is more and the number of charge carrier moving here is very less. So naturally what will happen? You are having some holes here and you are having some electrons here. There will be electron hole recombinations. Okay, there will be electron hole recombination. So if the injection of charge carriers are low, all the excess p-type charge carriers will recombine with the n-type charge carriers in the drift region. So if there are less number of charge carriers which are moving from p-type to n-side, all of them will be recombined in the drift region itself. But in our case, we are having heavily doping and we are providing proper forward bias. So because of this heavily doped characteristics, the delta P or the injection will be very high as compared to the charge carriers which are in the drift region or the electrons which are there in the drift region. So delta P is going to be much higher than ND0. So there will be some recombinations, but all of these holes will not be recombined. Okay, there will be some recombinations, but most of the holes will pass through this drift region and it will reach the n minus region. It will reach the border next metallurgical junction, which is n minus n plus. So it is starting in the p plus, it is moving across the p plus n minus junction, then it is finally coming in this junction, which is n minus n plus junction. So if the injection of charge carriers are high, which is in our case, excess p-type charge carrier distribution reaches the n minus n plus junction. It reaches the n minus n plus junction. So the question is, what is going to happen here? So you start from here and finally you reach a point here where after a little bit of recombination, most of the p-type charge carrier has reached the n minus n plus metallurgical junction. So what is going to happen after this? Now in the n plus region here, in the n plus region, let me just change the color of my pen here. So in the n plus region here, you are having a lot of electrons, right? You are having a lot of electrons because the n plus region is also heavily doped and the majority carriers in the n plus region is electrons. Okay, so you're having a lot of electrons in this region. And at this point, a lot of holes has reached the n minus n plus junction. A lot of holes has reached it. So naturally what will happen? These electrons will be attracted from the n plus region to the n minus region. Okay, so once holes reach here, holes reach the junction, electrons will be attracted from the n plus region to the n minus region. So here I have written that point. So once the holes reaches the n minus n plus junction, the electrons are attracted from the n plus cathode. This is the anode and this is the cathode. Okay. So this causes an electron injection into the drift region across the n minus n plus junction. Okay. So initially you had an injection of holes into the drift region. Initially you are having a injection of holes into the drift region. Now you are having an injection of electrons into the drift region. Okay. The question is, what would be the carrier density? Naturally, to maintain the electrical neutrality of this particular material, the charge carrier density of the p-type carriers would be same as the charge carrier density of the n-type charge carrier. Okay, so the charge carrier distribution of this would be same as the charge carrier distribution of the electrons. Okay, now what is the effect of this additional carrier injection? Okay, so you are having injection from two sides. one is the holes and one is the electrons inside the drift region. Okay, holes are coming from P plus and electrons are coming in from N plus. So what is the effect of this additional carrier injection? That we'll see in the next slide. So what would happen here? Naturally, what would happen is that the excess charge carriers diffuse and recombine in the drift region. The recombination is going to happen inside the drift region. Now, here one important concept we have to understand, which is the width of this depletion region. Okay, and the comparison of the width of the depletion region and the diffusion length of the charge carriers. Okay, so what is the diffusion length of charge carrier? Diffusion length of charge carriers. So basically, you know that diffusion length of charge carriers is the maximum length. Okay, it's the maximum distance a free charge carrier or a charge carrier can move before it undergoes recombination. Okay, so after that distance, it will recombine. Okay, so that is the maximum distance and charge carrier can move before recombination. So the width of the depletion layer is much higher than the diffusion length. Naturally, all the holes would be recombined in the diffusion layer itself. There will be no double injection phenomenon which is going to happen. Whatever electron hole has moved into the diffusion region, it would just have recombination within the diffusion region itself. So it is important that the width of the diffusion region is much less than the diffusion length of the charge carriers. Now, if that is the case, that is the width of the drift region is less than the diffusion length of the charge carriers, the spatial distribution of the excess charge carriers in the drift region will be flat. So for understanding this concept, we have to understand what is the spatial charge distribution of different type of charge carriers here. So to draw that, let us start with the charge carrier distribution of the drift region in the equilibrium condition. Okay, so we are doing the charge distribution in the equilibrium condition for the drift region. Okay, so in the drift region, you know that it is lightly doped. So naturally the concentration of electrons will be much higher than the concentration of holes, because holes here are only minority carriers. Okay, so let me just take a reference point here first. And let us draw the concentration of holes. Let this be the concentration of electrons. Sorry, let me take a different color pen for electrons. So let this be the charge carrier. Okay, charge distribution of electrons or the n-type charge carriers in the drift region at equilibrium. Okay, that is at this height. Naturally, the holes will be a little bit less. The holes will be less, right? So this will be the p-type charge carriers in the drift region at equilibrium, right? P-type charge carriers in the drift region. Now, let us draw the charge concentration of the P plus material. Okay, so this very similar to what you see in a diode. So you start at this region here. The majority carriers will be very high in the forward bias condition in the depletion region, you know that. So let me call this as PP. So this is the majority carrier concentration of the P plus, that is the p-type charge carriers. Okay, so remember, for holes I am using red and for electrons I am using blue color. So naturally I have seen here in the drift region there will be very less, in this region there will be very less recombination with these electrons, right, with these electrons. So naturally the distribution will be something like this. Similarly for electrons, here the concentration will be very high, because in the forward bias condition at the depletion region, the concentration of electrons of the n plus region will be high at this point, and here also it will be something like this. And once these electrons come into this area, here they will be undergoing recombination. It will become something like this. Similarly, distribution of the p-type charge carriers in the, because here it is becoming the minority carriers, right? So it will be something like this. But look at here. Look at this point here. Initially, the charge carrier concentration was this. At equilibrium. But now look at the charge carrier concentration. Now the charge carrier concentration has increased by orders. The charge carrier concentration has increased by order. That is, you can see that here clearly the space charge distribution is flat. Okay. Now, what is the consequence of this increased charge density? I hope it's clear. You can see that there is a increased charge density. Naturally, when charge density is going to increase, that means there are more charges, that means the conductivity will increase. When conductivity increases, that means the resistance will be dropped. That means in the forward mode, in the forward on condition, the resistance of the drift region will be very less as compared to the resistance calculated based on geometry and thermal equilibrium charge carrier densities. Okay, so this process is called conductivity modulation, right? The reduction of the resistance in the forward condition in a power diode in a drift region is called conductivity modulation. And this injection which is happening from both sides, from the hole side and the electron side, that means two injections are happening. This is called the double injection. And due to this double injection, you are having conductivity modulation, change in conductivity, and due to this conductivity modulation, the conductivity in the drift region increases and the resistance in the drift region decreases. Okay, so I hope I'm clear. The next video we will see what is the actual voltage current characteristic in the forward condition. So let's conclude the video today, and I'll see you in the next video. Thank you.